In this module, we introduce the activated complex theory, also known as transition state theory. Earlier, while discussing potential energy surfaces of reactive chemical systems, we introduced the transition state. It is the saddle point between the energy values of reactants and products on the potential energy surface and, from the other perspective, the position of the potential energy maximum along the reaction coordinate. The activated complex is a chemical species, a specific arrangement of atoms formed in the transition state. As such, it is the chemical system as it exists at the transition state. In this module, we turn to a theoretical framework for describing reaction rates developed primarily by Henry Eyring in the 1930s. This theory is known as activated complex theory or transition state theory. It provides a detailed and physically grounded description of reaction rates using the concept of a transition state in combination with ideas from statistical thermodynamics. The activated complex theory is based on the following key assumptions. First, that the reactants and the activated complex are in equilibrium. Second, that the reaction coordinate describing the decomposition of the activated complex can be treated as a single energetic degree of freedom. Let us return to our example, a bimolecular reaction considered in the previous module. Here you can see the overall chemical equation of this reaction, showing only reactants and products. Here, AB and BC are stable molecules, while we assume that the triatomic species ABC and the diatomic species AC do not form as stable compounds. If we look at the details of this reaction, we discover that this transformation proceeds through a high-energy configuration known as the activated complex. We can summarize the entire process, the reaction mechanism, with the following reaction scheme. In this reaction, atom C approaches molecule AB. The bond AB weakens while C forms a bond with B. Together, AB and C form the triatomic activated complex ABC, which then proceeds through bond rearrangement. The bond AB weakens further while a new BC bond is getting stronger. This leads to the formation of the new BC bond, breaking of the AB bond, and release of the atom A. Energetically, this reaction mechanism can be illustrated by the reaction coordinate diagram, which represents how the potential energy changes as the system progresses from reactants to products along the reaction coordinate. When atom C approaches AB, the potential energy of the three-atom system rises. It reaches a maximum at the transition state before falling again as the new molecule BC is formed and A is released. The rate of the reaction is determined by how quickly the system crosses the transition state on its way to the products. To apply activated complex theory to a specific reaction, we need to figure out three major aspects. First, we need to calculate the potential energy surface of the system, establish the reaction coordinate and the potential energy of the reactive system for various configurations of the atoms along the reaction coordinate. Second, we assume that an equilibrium exists between the reactants and the activated complex. And third, we must determine the rate at which the activated complex crosses the energy barrier. That is, the rate at which it proceeds from the transition state to the products. These elements together provide the basis for calculating the rate of a chemical reaction from first principles. We now describe the reaction in two steps, as done in the framework of the activated complex theory. The overall transformation AB plus C forms A plus BC can be represented by the following reaction scheme. In this scheme, the reactants first form the activated complex in a rapid pre-equilibrium. The second step is the decay of the activated complex into products. The equilibrium between the reactants and the activated complex is essential because it allows us to relate the concentration of the activated complex to those of the reactants. This approach enables us to apply kinetic approximation methods to determine the rate of product formation. Assuming that the activated complex forms in a fast pre-equilibrium, we can now write the corresponding kinetic expressions. This means that the rate of change of the reactant concentration is essentially zero. In this expression, the rate of the forward reaction depends on the concentrations of AB and C, while the rate of the reverse reaction depends on the concentration of the activated complex. Rearranging this equation gives us an expression for the concentration of the activated complex. Here, capital K double dagger is the equilibrium constant for the formation of the activated complex from the reactants. The overall reaction rate is determined by the rate at which the activated complex breaks down to form products. This process is described by the rate constant K2, which governs the conversion of the activated complex into the products A and BC. Substituting our earlier expression for the concentration of the activated complex into the rate equation, we obtain the rate of product formation as K2 times capital K double dagger times the concentrations of AB and C. We can define a new rate constant, small k double dagger, which combines the equilibrium constant for the formation of the activated complex and the rate constant for its breakdown. So the overall reaction rate becomes small k double dagger times the concentration of B and C. This expression for the reaction rate has the form of the rate law for a bimolecular reaction, but the rate constant is now derived from intrinsic molecular properties of the activated complex. In this expression, both constants capital K double dagger and K2 have far-reaching physical meanings. The equilibrium constant K double dagger describes the formation of the activated complex from the reactants. Its value can be estimated using statistical thermodynamics by evaluating the partition functions of the reactants and the activated complex. This approach allows us to incorporate molecular properties such as vibrational and rotational contributions into the calculation of the reaction rate. The constant K2 describes the rate at which the activated complex converts to products once it is formed. It is typically approximated as the frequency with which the system crosses the energy barrier along the reaction coordinate. The corresponding physical process is roughly equivalent to the vibrational motion along the reaction coordinate. A proper derivation of these two quantities requires more advanced methods than those introduced in this course. Nevertheless, activated complex theory provides a theoretical foundation for understanding reaction rates and their relationship to molecular structure and energy landscapes.